Now that we know the definition of an open set and a closed set, let's move on to the next definition, a compact set. And here's the definition. It might look a little bit confusing, but we'll draw some pictures in just a minute that make it a little clearer, hopefully. A set E is compact if for every family of open sets, this is the family of open sets, that has the property that E is a subset of the union of those open sets, there exists a finite set. Notice what these elements are. They're subsets of the index set capital A, or they're elements of the index set capital A, such that E is also a subset of the union of this much smaller number of sets. Right here, this finite number of sets. This means, in other words, E is a subset of just this 1, 2, up to n, the union of those sets, those n sets. So the index set here, alpha, could be, well, it could be all real numbers. There could be an uncountably infinite number of sets that we're defining here. It could be that A is the natural numbers, which means that this would be a collection of open sets, G1, G2, G3, ... would all be open sets. So, if the union of all those sets contains the set E, in other words, E is a subset of that union, and if for every such set there's a finite set that will also contain, the union will also contain set E, then we've got a compact set. So, rather interesting definition. There is a more informal way of saying this, where you could say E is compact if every open cover contains a finite subcover. E is compact if every open cover contains a finite subcover. What the open cover is just a collection of open sets whose union contains E. So this would be the open cover. If every such open cover of the set E contains a finite subcover means just take a finite number of these sets. If you can find a finite number of those sets whose union also contains E, well, then we'll have a compact set. So every open cover contains a finite subcover. Let's just do a very simple definition where I'm not going to, or a simple example, I'm not going to go in, try to even resemble an image that has an infinite number of sets as the open cover. But let's take the interval from 0 to 1. The open interval. So you could graph that on the real line like this. And I could have made these open circles if I wanted to, because this set does not contain 0 or 1. Let's just write a cover, an open cover. One open cover I can think of would be this collection of sets. 0 to 3 over 4, the interval from 0 to 3 over 4, open interval, and I could even go from 1/4 to 3/4. And the last one I'll say goes from 1/2 to 2. Okay, sorry, I wrote those different sizes, it looks like. All right, well, hopefully you'll all agree that if I union these three sets together, that union of the sets of these three sets would contain this. In other words, the interval from 0 to 1 is a subset of the union of these three sets. You can picture that 0 to 3/4 goes to about there. 1/4 to 3/4 goes about there. That set didn't really contribute anything, did it? If we union these two together. And then 1/2 to 2 would look something like that. So this interval is completely contained in the union. And so this is a finite cover already. But this cover does have a subcover, which means a proper subset of these whose union also contains the interval from 0 to 1. Remember I said this one didn't contribute anything? Because if I simply go from 0 to 3/4 and take the union of that and this, I'm going to get the interval from 0 to 2. Whether I take the union of all three or just take the union of this one and the third one, I'm going to get the interval from 0 to 2. So one subcover would be 0 to 3/4, that first element, and then the third element, 1/2 to 2. So all I've done here is I took a finite cover and I found a smaller finite cover of the set 0 to 1.